All right. So what we're dealing with, once I get the freaking Flowworks tools out of the way. Whatever, good enough. All right. So eventually this video will start. Maybe. Well, there was a video, but screw it. So, circular motion. Yes, it was a cat on a record player, which is just all sorts of entertaining. All right, so circular motion. Basically, what we're talking about here is what happens when things are moving in a circle. Okay, so if you remember the frames of reference video, when they had the entire room spinning, right? So what happened to the puck? Came back to the person, remember? So like they pushed it and it went full circle and came right back. So when things are moving around in a circle, when things are rotating, things happen to be a little bit different. If you remember with frames of reference video, there are two types of frames of reference. Remember. The inertial frame and what? There's the inertial and non-inertial frames of reference. I know. In physics, we are huge on naming things, and I'm going to die because of that back then. It has to do with your inner ear. Inner ear. You basically got liquid in your ear that helps you determine your orientation. Yes. Fantastic. All right. The point is, if you think about it enough, everything about the human body is kind of disgusting. Let's face it.
It's all in there.
Do it.
All right.
Do it.
Stop. All right. So here's the thing. When we are talking about circular motion, an object that is moving circularly is always accelerating, all the time. Because what is acceleration? A change of speed, or what's another word for speed? Velocity. Acceleration is a change in velocity. All right? So how can we, what makes up velocity? How can we change that? You can change the speed, or you can change the direction. Now, I'm gonna take my little turntable over here. Take my turntable. And I don't happen to have a nice giant arrow, but why not go ahead and use a meter stick? All right. All right. Let's see if I can avoid taking things out. So this meter stick represents the direction I'm moving, right? It's a direction of velocity. It's pointing in the direction its velocity is going, correct? Falling onto my laptop. It would make me a little sad. New-ish. Am I speeding up? No, but is my direction changing? So I'm still accelerating, right? I can't speed up. It felt like it. All right. So, not speeding up, but changing direction. So by moving in a circle, you are automatically accelerating, which means is it possible to be at equilibrium and moving in a circle at the same time? Well, equilibrium means no acceleration. So since you cannot move in a circle without accelerating, you may not be at equilibrium and moving in a circle at the same time. So we got a couple new terms we're going to get. This is also going to be the time where we're going to get the most new equations. The thing is, a lot of these equations aren't actually new at all. For next period. All right. A lot of these equations are new. For example, take the equation VF equals AT plus V naught. We are going to get the new equation omega final equals alpha T plus omega naught. Looks pretty similar, right? Because it's the same thing. The only difference is instead of velocity acceleration and velocity initial, we have final angular velocity equals angular acceleration times time plus the initial angular velocity. So we have to talk about angular velocities, angular rotations, angular displacement instead of linear velocity, momentum, displacement, all those kinds of things. So the fact that we're moving in a circle means we have to change those a little bit. Which means we have to break out circles and the radius of a circle quite a bit and circumference of a circle. Just got to think a little bit differently. But otherwise, a lot of this stuff is going to wind up being pretty much exactly the same. So a couple things I do want to mention, though. Frequency and period. Where have you heard the term frequency before? Okay, wave, sound, anywhere else? Radio, sine, cosine. Right, okay, so let's talk about the sine, cosine period, or frequency. What does it mean? What does frequency mean? Okay. What about period? Where have you heard the term period before? Really, Andrew? Well, no, let's go with it. Where? Where? Other than English. Okay, first period. Sure. Everyone inevitably giggles when I ask, where have you heard period before? Period. Girls.
What?
Where do you think the term came from? Period is defined as the length of time for one complete cycle. From something happening to it happening again. Where do you think the name came from, guys? Obviously physics, exactly. Or just the fact that that's the definition in general. The Earth has a period. It has two, in fact. It's got its rotational period, 24 hours. If you stand on any one place on Earth, then every 24 hours and I think like 12 minutes, you will be at the exact same place circularly that you were before. There is the period of orbit, which means every 365.25 days, you'll be standing in the exact orientation around the sun. Well, not the exact, because there's some other things going on. But roughly the same place around the sun as you were before. It takes 365.25 days for the Earth to go completely around the sun. Okay? That's all period is. There is a relationship between them. We'll get to it a little bit later. But the basic idea is, let's say we start here. The time it takes to go around the circle one time, that's the period. How many times it goes around the circle each second, that's frequency. Yeah. It's not easy. That's it. Right now, our system of the calendar, when we get to daylight savings time, there's always a video I show you guys. But the way our calendar is set up, okay? So we've got leap years. Leap years come in part because a day is not exactly 24 hours. But we can't just fix that. So we have to keep adding things on. Because if you try and fix that, then there's not an even number of seconds in an hour, and then that gets complicated. So we partially fix that, because right now the way our calendar is set up, every 1,000 years or so, we will be off by a couple weeks. So they fixed that by, like, if you remember, probably not, but back in 2000, we didn't have a leap year. We should have, but we didn't. Because at the change of a century, when we should have a leap year, we don't. So we have a leap year every 4 years, unless it's 1800, 1900, 2000, 2001, 2100, 2200, no leap years those years. And that makes the calendar more accurate, but it still will get off every 15,000 years or something like that. it's because the numbers don't work out perfectly unless you have decimals for hours. Like, I'll meet you at, 1.2 o'clock. It doesn't work that way. Even then, you have to get a fraction of a second. It's easier to just do it. Oh, that didn't answer your question at all. Fantastic. What was it?
I'm told my wife, anybody like wait for just what the amount of time per second. Like a second is a second long.
Sure.
Why don't we just make it like a little bit?
Because it doesn't divide evenly. Like, that was kind of my point of, you would still have to get into fractions of something. So even if you changed a second to be, if you define a second as, so there are precisely 30,000 of them in one day, exactly, not to mention the fact that the rotation of the Earth changes. That giant tsunami we had in Indonesia a couple years back, and actually because of something we're going to talk about, angular momentum, because it changed the distribution of mass around the Earth, it actually has made the day longer. Actually made it shorter. Whatever. It's off by a couple of milliseconds. So then we're going to completely change your calendar to get that happen. If we get hit by an asteroid, that's going to change the orbit of the Earth's level. So you're going to change it that way. Like, we just do the best we can, and we hang on. Whatever. All right. So we talked about this. The displacement is just some distance between here and here. We don't worry about the arc length, but the velocity does change because the directions change. So we've talked about that. Wait, hold on. What am I doing? All right. So going with that, I really need to redo this PowerPoint. I'll probably do that tonight, so you guys will get a little bit better one tomorrow. But here's the deal. We got to talk about how we're going to deal with acceleration. Because we're going to have something called angular acceleration. Basically, what is the acceleration that's keeping this thing moving in a circle? So basically, here's the deal. What we're saying is we've got two vectors. Your initial velocity, your final velocity. They're pointing in two different directions. And so if you add them tip to tail, then this vector here is your change in velocity. And what do we call change in velocity over time? We call that acceleration. So basically what we're going with is we've got, what do they do here? The radius of the circle, this is an isosceles triangle, right? What can you tell me about the magnitude of my two velocity vectors? The length of them. Equal. The speed's not changing, right? Just the direction. So I've got two isosceles triangles. What does that mean I can do? They're similar triangles, which means I can break out some geometry proofs. So what I can say is my change in velocity, this side, the ratio between my change in velocity and one of my velocity vectors is the same as my displacement to my radius of my circle I'm traveling in. Does that make sense? And I can set those equal to each other because they are similar triangles, so I can say their ratios must be equal. Right? I've got the same angle between them, all that kind of fun stuff. So if I play around a little bit, I can say, you know what, I don't like displacement. Displacement's ugly. But what's another way I can describe displacement? Velocity times time, specifically velocity times a change in time. So I replace my displacement with how far I went and how long I had. And by playing around a little bit, well, I notice I've got two V's here, so I want to do some cross multiplication. So I've got delta V times R is equal to V squared delta T. If I divide the R and the T's over, all of a sudden I get delta V over delta T is equal to V squared over R. Wait a minute, delta V over delta T. That sounds an awful lot like acceleration. So we have an equation for the linear acceleration of a rotating object. And the linear acceleration of that object is equal to V squared over R. The velocity of my object squared divided by the radius the object is moving in. The radius of the circle the object is moving in. Make sense? All right.
You know what? No. You had